Thank you to the organizers for the invitation to come to Lumini. It's always a pleasure. In spite of Mike's introduction, I will be doing the easy thing in this lecture, and that is, rather than prove a refinement of the ABC conjecture, I will give a refinement of the ABC conjecture. That is, I will give another conjecture. But anyway, okay. So let me set the stage here. A bit of notation. So for any positive integer n, we'll let k of n denote the greatest square free factor of n. So in particular, k of n then is just the product p divides n of the primes p, which divide n. That's k of n. And of course, the ABC conjecture is this absolutely marvelous conjecture due to Oesterle and Masser from 84, 85. And what did they, so this is the ABC conjecture, of course. What did they conjecture? Well, for each epsilon bigger than 0, there exists some positive number, which depends on epsilon, such that if A and B are coprime positive integers, then what? Then C is bounded from above by A0 epsilon k to the 1 plus epsilon, where C here is, whoops, C is the sum, A plus B, and K is just shorthand for the greatest square free factor of A times B times C. And of course, as we all know, this has incredibly profound consequences for the study of Diophantine equations and for a number of other arithmetical questions. And the reason that it's as significant as it is that in a sense, it captures in a very succinct way the idea that the arithmetic and the multiplicative structure of the integers are independent, and as a consequence of that's something that one believes that it's incredibly useful as a tool. Well. Okay, so of course one would like to prove it. And what can we say here? Well, if we've got this assumption that A and B are coprime, our standard assumptions, then what can one prove? Well, the fact that C is bounded from above as a function of K, the first explicit bound was a result we had with Rob Tiedemann back in '86. And the following is a result of you and I, and I always like saying that, I must admit. But what is it? Well, it's the following. There exists some positive number A1 such that with the usual assumptions as above, C is bounded from above by the exponential of k to the 1/3 log k cubed, and we can throw our a1 in here, say. Where, again, k is the greatest square free factor of ABC, and a plus b is equal to c. Okay, so of course, this is a long way from the truth. Nevertheless, it's at least an upper bound in terms of what we suspect the truth to be. It's at least an upper bound in terms of k. What are the ingredients in the proof? Well, the proof depends on estimates for linear forms and logarithms, and one uses a result of Matveyev in the complex case, and in the p-adic case, one uses a result of Kunri-Yu, so one needs to take into account both of these results. And one can ask, well, okay, can we push this further? And basically, one would hope to replace that k to the 1/3, at least within this context of linear forms, by a k to the epsilon for any epsilon. And the sticking point here is in the p-adic estimates for linear forms and logarithms, and it's the dependence on the prime p in those estimates. And that seems to be a sort of a fundamental problem. One can improve this slightly. One can improve the second order term, but I don't see any way at the moment of pushing that factor of 1/3 down. Well, of course, there is the result of Mochizuki, which is the claim anyway, which we'll still wait to be to see whether it's verified, and that would of course give the full ABC. So there is that conjecture out there, but at the moment at least we can get certainly within this distance of true ABC. Okay, well, one can look at the ABC conjecture and ask for various modifications or refinements of it, and this is something that has been considered by several people. Baker has some versions, Van Frikenhuizen. And others. Let me mention a refinement proposed by Van Frikenhuizen. So in 2000, Van Frikenhuizen conjectured the following, whoops. There exist positive numbers A2 and A3 such that in the sort of first version of ABC. So here we're concerned about, this will be a refinement where we take into account what this k to the epsilon should be. So he conjectured that there exists positive numbers A2 and A3 such that if A and B are coprime positive integers. Let me just say then, C is bounded from above by k times exponential of a2 square root log k over log 2k with ck as above. And so this is a refinement, obviously, of ABC. And yes, it is the double log, but it's not quite the double log. Think of it as the double log, but let me just get to that in a second. And for infinitely many pairs, AB of positive integers C is bigger than k exponential of a3 root log k over log sub 2k. So in other words, this is at least giving us the right order of magnitude. And now let me come to Vadim's point, and that is I just want to avoid trivialities. So in this lecture, for j bigger than or equal to 2, log j sub x is the jth iterate of the map that sends x to the max of 1 and log x. We'll be looking at triple log x. I don't want to worry about when that's bigger than, when that's properly defined. Okay, so this is the result of, or the conjecture, I should say, of Frankenhuisen. And now, recently with Robert and Tenenbaum, we've come up with a further refinement and a justification for the refinement. So let me state our conjecture. So okay, so we've got our setup up here. We'll say there exist C1 and C2 real numbers such that if A and B are coprime positive integers, then C is bounded from above by, and now what do we have here? K, the exponential of 4 root 3 log k over log 2k multiplied by 1 plus log 3 over twice log 2k plus C1 over log 2k. So this is the upper bound, and then, of course, if one's going to do something in this precision, well, the expectation is that one hopes that these terms are necessary. And let me just be a little, let's write that properly. So this square root is over 3 log k over log k. So that's the conjectured refinement of ABC. And further, there exist infinitely many pairs A, B of coprime positive integers for which C exceeds k exponential, well, the exact same thing for square root 3 log k over log k, and then we have the first two terms, log 2k, 3k over twice log 2k, and then a different constant here. Okay, so that's the refinement of the ABC conjecture that I would like to speak about. So we started off talking about upper bounds here, and it's reasonable to ask, okay, well, can we approach, we saw we couldn't get too close to the correct upper bound. Can we approach the lower bound, at least from below? Can we construct examples for which that is maybe not so implausible? And with Tiedemann, we proved the following. So there exist infinitely many pairs positive coprime integers A, B, for which C is bigger than k e to the 4 minus delta square root log k divided by log 2k. And in 2000, and Frankenhuisen showed that one could replace this constant 4 minus delta by 6.068. Okay, so we see, at least from below, we're getting fairly close to what we conjecture the truth to be. So in this expression, the square root goes over the log k term. In this construction, we miss out. We only get it to within a log k. Okay, so that's the conjecture. Let's see. So I need some more boards. So let me pull this one down and start on this. Of course, there's been, it's natural when one has a conjecture like the ABC conjecture to do some testing, to do some numerical work and see what stares us in the face. And the very first thing people did was try to see if the exponent 1 was the correct exponent, or 1 plus epsilon. And that's the initial sort of computations have been vastly extended, and there's a distributed computing project at the University of Leiden with Bart de Smet in charge of it. And it's called Reconnaissance met ABC. And this is one of these computer projects where it can be pieces of it can be farmed out to individuals with computing power that's just going unused. And he keeps track of it, and I think they've got all, they've worked out the bounds for K of C for all pairs AB up to, with C up to at least 10 to the 18, I believe now. And what you want to do, well, of course, the ABC conjecture is concerned with pairs that are exceptional. And so in this vast computation, you're looking at the exceptional points here, and there has to be some way of measuring whether a pair AB is exceptional. And so there's two quantities that have been introduced. The quality, which is just log C over log K, and the merit, let's say M, which is Q minus 1 squared log K over log K. And the quality, so this is really testing whether 1 plus epsilon is the right order of magnitude. This one is the right order for that first power. This is testing whether, well, the way it's written, 4 root 3 squared equals 48, whether that's the correct exponent. And the best results found here for the quality, well, it's an example due to Eric Ressa, which has Q about 1.6299. And then Bene de Weger has an example, 1.6260. Well, this is approximately. And those are the largest examples in terms of the quality which are known. And it's interesting to see that if you look at the tables of associated with this Reconnaissance met ABC project, you see that the examples seem to, in terms of the quality seems to be slowly moving down towards 1, but really quite slowly. But it does seem to be moving down. And so this may be the ultimate exception, but we're a long way, obviously, from knowing that. In terms of the merit, so that's asking whether 4 root 3 is the correct exponent. Something different is happening because the small values, pairs with A and B small, don't give you the largest merit. The merit seems to be increasing, and so the best known example is a merit of, it's a triple found by Ralph Bons with a merit of around 38.67. And again, so the opposite phenomena seems to be exhibiting itself, that you have to go farther and farther out to get closer to this factor of 48. Okay, well, what's the underlying motivation for this refined conjecture? Again, it comes down to this notion that the additive and the multiplicative structure of the integers are independent. And what we want to do, if we want to really examine that notion, we need to consider the function n of xy, which counts the number of positive integers n with n less than or equal to x and k of n less than or equal to y. And this function, it's a very natural function to study. It's the analog of the de Broglie-Dickmann function psi of xy, which counts the number of positive integers up to x whose greatest prime factor is at most y. And that's been extensively studied and repeatedly used. Now, that situation's a little nicer because if you have the greatest prime factor of A is less than or equal to y, and the greatest prime factor of B is less than or equal to y, well, it's also true that the greatest prime factor of the product is less than or equal to y, and that certainly doesn't apply for the greatest square free factor. So technically, it's much more difficult to analyze this function, and this was basically everything one would want to know about the behavior of this function has been determined in an absolutely magnificent paper, a real tour de force of Robert and Tenenbaum, where they used the saddle point method to really get a handle on how n of xy behaves. So n of xy, right, let me see. So basically, what I would like to say about n of xy is the following. How does it behave? Well, let's put v equal to log of x over y. What Tenenbaum and Robert prove is that f of xy behaves like y f of v over a large range of x and y. So this is Robert and Tenenbaum. Okay, and in particular, sorry, this is not, excuse me, n of xy, there we go, is behaving like y f of v. Now I have to tell you something about f of v. F of v, what they prove is there exist polynomials qj, and let's say polys qj of degree at most j, for j equals 1, 2, etc., so that f of t looks like exponential of square root of 8t over log t times 1 plus sigma j goes from 1 to, say, capital N of qj triple log t over log 2t to the j, plus we need a big O term, which is triple t over double t to the n plus 1 for any n. Okay, so essentially what one has to do, I mean, this is the start, but the idea is that, well, we model the behavior of the greatest square free factor of k of a sum a plus b. Statistically, we'd like to think that it's behaving like just a typical integer of size a plus b. And so with this sort of basic assumption, which I can make completely explicit for you, but we're out of time, one starts with that hypothesis, and then using this work of Robert and Tenenbaum, one can proceed to prove that from what seemed like an extremely reasonable hypothesis that at least statistically Ka plus b is behaving independently of Ka and Kb, using the analysis Robert and Tenenbaum have provided for us of the behavior of the function nxy, going through that, one arrives, and Rankin's method, one arrives at this upper bound, and similarly, it's a little more refined, but one can also obtain this lower bound. And I think I'll stop there.
Point of Q is 1.
Without any conjecture, yes, that 1 is a limit point in there. Exactly. I'm not sure of that, but don't you have a paper with Filosata and several others concerning this question?
Just this question we have not